Welcome back to the NExT Appraisal Tool modules. In this module, we'll be discussing question 16, are the statistical analyses clearly described? When answering this question, look for the Methods section, and often articles will have a separate section labeled Data Analyses. First, let's talk about data and variables. Variables represent anything that has a quantity or quality, and they're called variables because they vary. They're expected to differ in the amount or type. An independent variable is expected to cause a change in the value of an outcome. This is typically manipulated by the researcher. And then we have the dependent variable that is expected to change. Data are the values of each of these variables. Data analysis is just the organization and testing of information to answer a research question. As you read an article, the author might also mention confounding variables. Confounding variables are factors that may influence both the independent or dependent variable. The presence of these factors introduces alternative explanations for the change in the dependent variable, and therefore would reduce the validity of the study results. In other words, the researcher might find a relationship between the independent and dependent variable that does not exist because the confounding variable caused the change in the dependent variable. As a clinician, you need a general understanding about the data collected and the statistical test used to examine these data. There are 4 levels of measurement used to assign numbers to information collected and determines the type of statistics we can use. They are ranked from the lowest to the highest level of data, or the least amount of information to the most precise amount of information. Nominal is the lowest, ratio is the highest. We can use more advanced statistics with the more precise data, the ratio. Nominal refers to categories of information, such as whether a patient has a specific diagnosis. Ordinal categories are just that. They're ranked in the order of amount, but the difference between each category is not exact. Interval categories are a higher level of measurement because these categories have equal distance between them. We know the exact difference between a Fahrenheit temperature of 100 and 101. Ratio data is the highest level of measurement, again because it's the most precise. Rather than simply knowing whether someone is pre-diabetic or diabetic, we have a precise value of their serum glucose. Descriptive statistics summarize information and are used to describe the characteristics of the study sample and outcomes. The count is the number of times a value occurs. A frequency table is typically reported with the count and percentage of each value. The center of the data is described using a mean, a median, and a mode. They tell you about the center because the mean is the average, the median is the number that falls in the middle when the numbers are sorted from smallest to largest, and the mode is the number that occurs most often. This figure shows a typical bell-shaped curve, which is a normal distribution. You see that the mean, median, and mode all fall in the center. Variation or spread of the data are described using the range, standard deviation, and variance. The standard deviation is just the average distance of the values from the mean value. The variance is standard deviation squared. You will not need to calculate these. Just know the larger the spread of the data, the larger each of these statistics. There are many statistical tests that require a normal distribution to produce valid results. Authors will typically report if their data were not normally distributed, and if so, which statistical tests they chose to ensure their data were valid. In statistical testing, there's a null hypothesis and an alternative hypothesis. The null assumes there is no relationship, that the intervention is not effective. We assume the null is true and the statistical tests are conducted to determine if we can reject the null hypothesis. We can never know with absolute certainty whether results are accurate. There's always a possibility of making an error. A type 1 error is consistent with a false positive test. We reject the null hypothesis, but there really is a relationship. A type 2 error is consistent with a false negative. The researcher reports there is no relationship, but there is. In an article, the author will also report the alpha. This indicates the probability of making a type 1 error. Researchers commonly set the alpha at 0.05. This means there's a 5% risk the test results are the result of a type 1 error. Related to the p-value is a confidence interval. If the significance level is 0.05, the corresponding confidence level is 95%. This is simply the range of likely values for a population parameter, such as a population mean. A 95% confidence level means that there's a 5% chance that the test results are the result of a type 1 error. To determine statistical significance, we look at the p-value, or the confidence interval, of the observed data. A p falls between 0 and 1. If the p-value is less than the significance level, the alpha, or the confidence interval does not contain the null hypothesis, a 0, the results are statistically significant. In general, the smaller the p and the more narrow the confidence interval, the more confidence we have to reject the null hypothesis. Power is the probability of not making a type 2 error. High power is good. During planning, power is calculated and also takes into account the effect size. This refers to the estimated size of the difference between the groups, or the change in the dependent variable. The larger the effect size, the higher the power. A power of 80% means the author has an 80% chance of not making a type 2 error. If the purpose of the study is simply to describe a phenomenon such as the prevalence of disease, then there's no hypothesis and no statistical testing. The author will use descriptive statistics such as means and percentages to describe the information collected. Researchers use inferential statistics shown in this table to test study hypotheses. Inferential statistics use the values in the sample to estimate the values in the larger population. So when testing a hypothesis, we have to also consider the measurement level. Looking at the test for differences between groups, a very common test is the chi-square that compares differences in proportions. A t-test will examine a difference in a mean between two independent groups. An ANOVA is an extension of the t-test in that it allows the comparison of mean differences between two or more groups. The ANCOVA differs from the ANOVA in that it controls for potentially confounding variables that might lead to inaccurate results. Associations between two variables can be tested using the Pearson's R. This identifies the strength and direction of a relationship between two continuous variables. It can only examine an association and cannot determine if one variable causes a change in the other variable. Relationships among two or more variables can be tested using regression and other types of modeling to predict outcomes. Logistic regression uses a dependent variable that has two categories, such as yes or no, whether my patient has hypertension or not. Linear regression uses a continuous dependent variable, such as depression score or birth weight. As mentioned earlier, the distribution of data helps determine statistical test. When data fall into a normal distribution, parametric statistics are used. When the distribution is not normal, It uses non-parametric tests. Examples of non-parametric tests include the Mann-Whitney, Kruskal-Wallis, and Friedman. Clinical trials might analyze the risk of an outcome. This tells us about the size of the effect of an intervention or exposure. Risk typically refers to the probability of an adverse outcome, but it can also tell us about the risk of a favorable outcome. Absolute risk is expressed as the percentage of the total number of people in each study group. It is the percentage of people who have the outcome in a study group. Absolute risk reduction is when the risk of an adverse outcome is lower for the intervention group than the control. For example, if the absolute risk reduction of receiving a new treatment to reduce breast cancer is 8%, then 8 out of 100 people would benefit from the intervention. Relative risk compares the risk between study groups and estimates the effect size of the treatment. If relative risk equals 1, there's no change. If relative risk is less than 1, then the intervention lowered the risk of the outcome. If relative risk is greater than 1, the higher the risk of the outcome. One more way to understand risk is looking at the odds ratio. It's the odds of the outcome occurring in the intervention group divided by the odds of the outcome occurring in the control group. Consistent with interpreting relative risk, if the odds ratio is less than 1, there's a lower risk. If it's equal to 1, there's no difference, and if it's greater than 1, there's a higher risk. Authors should clearly describe how each of these is calculated. Here are 2 additional results that tell us about the likelihood of an outcome when exposed to an intervention. Number needed to treat is the number of individuals who need to be treated to prevent one adverse outcome. If the number needed to treat is 5, that means that every 1 in 5 individuals will benefit from the intervention. Number of needed to harm is the number of individuals who need to be treated for one individual to be harmed. That might mean it's negative side effects. If the number needed to harm is 65, for every 65 individuals receiving the treatment, 1 will be harmed. We want our interventions to have lower number needed to treat and higher numbers needed to harm. A methods section may also describe a power analysis. As mentioned earlier, power is the ability to reject the null hypothesis that there is no difference or that the treatment will not work. A description of the power analysis should contain the amount of power selected, and the standard is 80%. It should contain the alpha, the expected effect size, and the sample size. Authors will often predetermine their sample size based on the number of participants required to detect a difference between study groups or to detect a relationship between variables. It's easier to detect a statistical significance when the effect size is larger versus smaller and when we have a larger sample. Larger studies are also able to detect smaller effect sizes. Statistical significance is different than clinical significance. Clinical significance is the practical importance of the study results. They have meaningful impact on healthcare decisions and the health and well-being of our patients. For example, an exercise intervention for adults with BMIs greater than 30 that generates a 500-gram weight loss for the intervention group might reach statistical significance, but this small change may not be clinically meaningful. Will a 500-gram loss affect healthcare decisions about which medication to use or potentially reduce hypertension? That's what you have to think about when you look at statistical significance. Do these findings impact patient care? Here is a passage from a published article to help us answer the critical appraisal question, are the statistical analyses clearly described? You may wish to take a moment to pause the presentation, read over the passage to find the answer, and when you're ready, restart the video to see how I answered. In forming your appraisal response, decide if you think the authors clearly described data analysis. While you might not remember these exact tests, this author provides detailed information that would allow you to look them up and refresh your memory. If the author leaves you questioning how they handled the data, you would answer no. When reading the full article to place this section in context, you will notice this author lists data analysis for each outcome. We see that the author uses means and percentages to examine feasibility, acceptability, and satisfaction, and they reported that they tested the effect of the treatment on hopelessness and physical activity by using t-test and chi-squared. All of these tests are consistent with the study purpose and the type of data collected. Congratulations! You successfully completed this module. You may return to the main menu or continue to other appraisal modules in the next EBP course.